welcome back. Now, we're spending some time today talking about internal sources of variability in the climate system and how they are responsible for a big chunk of the year-to-year or season-to-season variability in our climate system. And there's going to be lots of these sources of internal variability in the climate system. We're going to spend most of our time today on either monsoons, or the El Nino Southern Oscillation System, or on the quasi-biennial oscillation, also known as the QBO. We'll spend a little bit of time on other tropical phenomena and how they relate to higher latitude processes too. You might notice there's a little bit of a bias to stuff that's in the tropics here. That's a little bit of an interesting connection to when you read chapter 14 or whatever it is in the IPCC report. You'll notice that it's almost all tropical stuff too. And if you want to know more about any of these processes, tell your advisor you want, we need some demand to teach ATSEVS533 tropical meteorology, where, even though the name is tropical meteorology, it's really more like tropical climate. And I'd love to teach you, I love to teach students all about how monsoons work and how El Nino works and so on. But today we're going to just get a little overview of how each of these systems work and how they're being affected by forced climate variations. So the first of the internal climate variations I want to talk about are monsoons. Now, again, if you haven't had the tropical meteorology or tropical climatology course, you might not be that comfortable with the word monsoons. Monsoons are a seasonal phenomenon. They have an annual cycle to them, and they are responsible for producing most of the precipitation that happens, particularly the wet season precipitation that happens in the tropics. There's a little insight right in there that monsoons produce a climate regime where there is a wet season and a dry season, and specifically monsoons have the wet season in the summer and the dry season in the winter. Now, let's not get bogged down in that idea of winter and summer, because I know it's the tropics. You're thinking, how much winter and summer is there in a place like India or West Africa or something like that? Well, the answer is, just think about it in terms of which hemisphere we're in. If we're talking about the northern hemisphere tropics, then summer is like July and August, and winter is like December and January. Okay, I get it. That's not going to be all that much cooler in India in December than it is in August, but whatever. Okay, so there's a dry season in the winter and a wet season in the summer. It does have to work that way. There are parts of the world that have climate regimes that are the opposite, where they have their wet season in the winter and their dry season in the summer, but that is not a monsoon. That works differently. Monsoons are a fascinating phenomenon that, as we talked about a little bit at the end of Module 3, is fundamentally driven by the difference between the surface temperatures of continental land masses and the oceans around them. Now again, in the tropical meteorology course, we pick all apart about how that drives planetary scale circulations and so on. We just can't possibly pick that all apart in this one little course right here. But the message that we get is that we're going to get patterns of winds at the surface that then have a very strong annual cycle. In the summer, the winds at the surface are going to blow from the ocean towards the tropical land masses. And in the winter, the dry season, the winds are going to blow from the tropical land masses towards the ocean. Again, it's about the differences between the temperature. In the summer, the land is much hotter than the ocean around it, and in the winter, the land is much colder than the ocean around it. I realize that, it's hard to picture getting all that much colder. Again, cold by like India standards or West Africa standards or Central America standards or whatever. It's not cold like Omaha, but it's colder than it was in comparison to the ocean around it. Just to give you some examples of this here, I just kind of created some charts here. This is the mean wind vectors at 1,000 millibars, so quite close to the ground, in August. This happens to be a 20-year climatology, 1990 to 2010. You can see the label down there at the bottom of the figure there. And the wind vectors kind of show you the directions of the wind, and the colors there show you how the strength of the wind in meters per second. And because I know that they're shown kind of small there, I just highlighted the most important one with a big arrow in PowerPoint. And you can see that in August, there's this huge transport of wind. The wind is transported across the Arabian Sea towards India. Okay, in fact, it's very strong. The reddest color there is, 14 meters per second? That's like, 28 miles per hour or something? That's a very strong, persistent wind. In contrast, oh, by the way, and that produces precipitation. This map that I have this little inset here on is the precipitation at the same time, and it's just a little map of it with units of millimeters per day at the same time or something like that. And see how it's raining all over the place in India and Southeast Asia and so on, as air is being transported from the ocean towards the land. In contrast, like if we turn to, this is January, if you look at the key down here at the bottom, again, because the arrows are kind of small, I highlighted just one of them with a big PowerPoint arrow there, and you can see the wind blows now from the tropical landmass towards the ocean. So there's really no way to transport moisture onto the Asian continent at this time of year, and in fact, if you look at a map of that's January precipitation for the same time period there, you can see there's virtually no precipitation over the Indian subcontinent in January. Okay? This is the dry season. August is the wet season in India. We could do the same kind of game with West Africa. Okay, so again, because I know the plots are a little bit small and so on, and the arrows are strangely small with the software that I used, I illustrated it with a blue arrow, with a white arrow there. But this is again illustrating just the winds across Africa. And you can see that across West Africa, roughly where I have that arrow there, you can see that the winds flow from the Atlantic towards the continent during, and if you look at the key there, it's August. Okay, so this is an August mean wind for the period 1990 to 2010. And winds are in August towards the continent, transporting water vapor from the ocean towards the land. And in fact, if we, I got these slides a little out of order, I'll straighten them out when you watch the video there. If you make a map of precipitation in August, you can see that there's a band of precipitation all across tropical West Africa, extending pretty far north towards the Sahara, which is a little bit farther north than, up there where there's no rain. But if we compare that to, say, January, now in January we have these winds that are coming from the Sahara, across tropical West Africa, and then out towards the ocean. Like I have that one illustrated there. Again, the colors there are wind speeds. But if I put you at the same time there, let's see here, if I show you the rain, well, there's still rain, but it's mostly off over the ocean. There's very little rain happening over West Africa itself. There's a little bit right along the coast in this particular analysis, but by and large, there's not a drop of rain falling across most of West Africa. This is the dry season. Oh. So like if I compare directly, I've got the January panel here on the left and the August panel on the right, you can see how there's a big shift in where the rainfall is happening over the course of the year. This is an internal variability to the climate system. This is not happening because of the release of greenhouse gases. This is not happening due to changes in orbital parameters. This is the internal physics of the climate system. It produces these patterns of warming and cooling that make the continents in the tropics warmer than the ocean around them in the summer, but cooler than the ocean around them in the winter, that drive these large-scale circulation patterns that in turn change moisture availability and so on, such that we end up with shifting areas of precipitation between the summer and the winter season. It's an internal variability of the climate system. And in fact, it happens in all kinds of parts of the world. Now, it turns out, again, in my tropical meteorology class, oh my gosh, we can make like a whole lecture about the fact that there's no single best way to define where monsoons happen and where they don't. I grabbed this particular picture from the IPCC 5th Assessment Report, where they just illustrated, based on certain statistics, where they consider to be monsoon regions around the world. But you see, it's basically the tropical land masses. Okay, West Africa, South Central Africa, parts of South America, India, Southeast Asia, parts of Northern Australia, and so on. These are the parts of the world where monsoons happen. And, that's actually a big chunk of the total surface area of the Earth. And as we learned in Module 3, something like 1 billion people depend on these seasonal rainfalls for their water and their irrigation and to produce their foods and so on. This internal variability, of course, is not changing the forced variations, right? I mean, the rain pattern here shifting to the north in the summer and back to the south in the winter is not changing the rates at which we burn greenhouse gases. It's not causing volcanic eruptions or changing the output of the sun, but it can in fact be affected by them, right? Forced climate variations can be causing changes in these monsoon patterns, and we know that there's going to be all these important anthropogenic changes to the climate system. I mean, we've spent 3 modules of the course already picking out this idea, understanding the physics and understanding the numerical modeling that shows us that we're expecting higher temperatures, We want to have differences between, we're going to have changes in the difference between the land and sea temperatures. Excuse me, we're going to have more water vapor overall in the atmosphere, all of which will have an impact on the monsoon system and its internal variability. So what does that actually mean for how the monsoons themselves will be changing? Well, the IPCC did what they do. They review large numbers of studies. They look at the output of large numbers of models, like an ensemble of 42 models, and they get a sense of what's the range of possible outcomes and so on. And just to quote them, climate model projections through the 21st century show an increase in the total monsoon rainfall, largely due to increased atmospheric moisture. In other words, we know from earlier figures, we know that overall the atmosphere is more moist that's part of the water vapor feedback, if nothing else. And so they're saying as that circulation works with that moisture, there's just going to be more condensation and more precipitation. Climate models are projecting from 5 to 15% increase in the global monsoon precipitation, depending on which scenario. The RCP 2.6 versus RCP 8.5 and all those kinds of scenarios, right? The more anthropogenic warming we see, the more it affects the monsoon and the greater the increase overall globally that we get of monsoon precipitation. But it's more complicated than that. I mean, we've already seen that like the band of where the precipitation is happening moves north and south over the course of the year as part of the monsoon circulation. So if you're at a fixed location, the wet season comes to you, and then the wet season moves away, and you're under the dry season, right? You're under your first dry, then the rains come to you, then the rains move away. But we don't know, what if the rains now move farther north and south and they pass right by you? You know, you have a short period of rain, but now the rains are farther to your north. That's a problem. That's a natural thing that happens in some parts of the world, by the way, but we don't need to talk, again, take tropical meteorology. The total surface area affected by the monsoons is projected to increase. That means that they're expecting that region, that the monsoons move back and forth across to increase, along with the part of that general poleward expansion of what we call the tropics, the expansion of the tropics. Although total rainfall, tropical monsoon rainfall increases, there will be some areas that receive less rainfall due to the weakening of these tropical circulations. So you're going to see what that's all about in just a moment. But that's our first hint that the story of monsoons gets complicated fast. All of the monsoons work, the West African monsoon, the Australian monsoon, Southeast Asian monsoon, Indian monsoon, they all work in very related ways, but they all have their regional differences too, and we're going to start seeing that there's complications with regard to all of them. Monsoon onset dates, like when the rains start, are likely to be early or to not change very much, and the monsoon retreat date, the day that the rains move away from you, are likely to delay, which is part of the story why overall in the models we get longer monsoon seasons and more precipitation. But again, it's always a little dissatisfying that a big part of what we learn about from when looking at these models is that the effects are regional. Well, that's just life. I mean, there's complicated problems have complicated answers, and one of the things we're finding out is that these situations are complex. Some areas will have stronger monsoons, some of the monsoons will be weaker, some will be moving farther north and south, some will be moving less north and south. And astonishingly, some of these changes are already happening. We actually have good observations that some changes have already been happening in the monsoon system, particularly the Indian monsoon season. The Indian monsoon, some years are wetter, some years are drier. But overall, especially in the last 20, 30 years, the Indian monsoon season has been overall weaker. And we think we know why from a climate science perspective. It's the very creepy Asian brown cloud, or ABC. Now, the Asian brown cloud is not a cloud. It is not water vapor. It's yuck. It's stuff that's in the atmosphere over Asia. What is the Asian brown... Oh, sorry, let me go right over here. Sorry. The textbook I got this stuff from talked about it as being a haze layer surrounding the whole of like the northern Indian Ocean, much of South Asia, India, Pakistan, parts of Southeast Asia, and much of China. It's misleading to call this haze because haze is part of the story, but haze is more complicated than you might know. survivors of like an atmospheric physics class find out that haze is a complicated story about the aerosols that produce it, and they get swollen by water vapor that condenses on them, and it's a complicated story. Thinking of this as a haze is not helpful. This is in general just all kinds of weird anthropogenic aerosols that ended up in the atmosphere in that part of the world. Mostly mineral dust due to poor agricultural practices. I mean, that part of the world is largely going through a process similar to like the Dust Bowl in the 30s in the United States. And sulfate aerosols due to the incredible explosion of coal power in that part of the world. Okay? As that part of the world has industrialized rapidly in the last 30 years or so, there's been this incredible increase in the amount of coal-fired power in an area that has relatively weak regulation of the emissions, and so we have these sulfate aerosols. Both mineral aerosols and sulfate aerosols have a negative radiative forcing. From a global climate change perspective, that actually doesn't seem terrible because it helps relieve some of the positive radiative forcing associated with greenhouse gases and so on. But regionally, this is a big problem because what this means is the continent does not, this blocks solar radiation from reaching the surface of the Earth over Southeast Asia, India, Pakistan, and so on. That keeps the continent cooler in the summer. There's no longer so much of a temperature difference between the oceans, where the air is clearer, and over the land masses where there's now less heating. So this reduces the strength of the monsoon circulation and reduces precipitation. And this certainly has been studied extensively. This is a pretty well understood phenomenon. It's a big part of the reason why those parts of the world are working as hard as they can to reduce their emissions and to improve soil management practices and so on, because this Asian brown cloud, which has other impacts as well, health impacts and so on, is a major problem in terms of like water availability and so on. Yuck. Your IPCC report actually mentions this. They don't use the word Asian brown cloud as far as I can remember. They say, though, that the observed recent weakening tendency in seasonal rainfall and the regional redistribution of rainfall in Southeast Asia and India and so on has been partially attributed to factors such as changes in black carbon and sulfate aerosols, which is what we talk about like brown cloud, changes in land use, where they're talking about like, poor soil management practices and so on, and also sea surface temperatures. Now that's more of a greenhouse gas kind of thing where we're talking about, as the ocean around India warms up, well now again there's less of a temperature difference between the ocean and the land in the summer. All of these are contributing to the fact that we've had about 20-30 years of overall weaker monsoons in India. Let's talk briefly about another monsoon. Now, in the case of the Indian monsoon, we actually can model it with numerical climate models pretty well. We actually have a pretty good, the modeled monsoon looks a lot like the monsoon in the real world, both in terms of the winds and in terms of the amount of precipitation that gets simulated and so on. The question is, can we say the same thing about tropical West Africa? And the truth of the matter is we don't. In case you guys don't know, West African meteorology is what I do for my research and stuff like that. So I find it fascinating that while we understand global change and the Indian monsoon fairly well and how the Asian brown cloud affects it, we know a lot less about what to expect of the West African monsoon, in part because so much of the rain that falls in the West African monsoon falls in a particular type of small-scale severe weather phenomenon called a West African squall line. There's actually a picture up there in the inset there of a West African squall line. The leading edge of it has this really scary looking dust storm in front of it with a cool name. It's called a haboob. In case you have never heard of that term before, it even has that weird emphasis on it. It's a haboob. That weird dust storm that happens out ahead of them. This is what dumps most of the rain that falls in West Africa during the monsoon season, is these, what becomes fairly common rain systems that dump a lot of rain, but they're fairly severe as well. And it turns out those things are not really well forecast by the relatively coarse resolution numerical climate models. You can simulate with a numerical model, these West African squall lines. That's not really a problem. But you need to have pretty high resolution in your model to do it, I don't know, a kilometer or something like that at the best. You have a nice little regional model over West Africa, you can simulate the heck out of these things. The problem is, remember, the numerical models that we use for climate projections have to run for 100 years globally. They have much lower resolution, maybe 25 kilometers or something like that. Well, the whole squall line fits between 25 kilometers. You can't meaningfully simulate these phenomena with a climate model. So we actually don't know that much about what's going to happen to West Africa due to climate change. A fascinating little problem with what we know and what we don't know. All right. Before we move on and talk about the next phenomenon, which is going to be El Nino and the Southern Oscillation, let's answer 3 quick questions. Question 4. The wet season of a monsoon typically happens in A, the summer, B, winter. Which one is the wet season? Make a choice from those 2 options and get a little feedback before you move on to question 5.